So yeah, the pipeline is the biggest object. So let's do a pipeline here. I will try my best to explain what the pipeline more or less does. And I will use this as a reference, which is what I linked in the last tutorial. So in order to create a pipeline, we do vk create graphics pipelines. vk context device. Pipeline cache will be 0. The pipeline cache is some sort of cache that stores data about pipelines when they are being created. So creating another pipeline would not take as much time, but this can be important if you want to create a lot of pipelines very quickly. The call to create a pipeline is still very expensive though. It is one of the most expensive calls in Vulkan. The next thing that we need is a create info count. We can use this call to create more than one pipeline. We will create one pipeline and then a vk graphics pipeline create info. I call this pipe info. And then the allocator 0 and pointer to vk context pipeline. We specify the vk graphics pipeline create info, pipe info, initialize that to 0, vk pipeline, put that into the vk context. And let's look at the pipe info, which will be a shit ton of stuff. Obviously, we need the S type, graphics pipeline create info. We need a lot of stuff. We need color blending state. We need input assembly state. We need multi-sample state, we need rasterization state, tessellation state, we need viewport state, vertex input state, render path, thankfully we have that. And in our case, we also need dynamic state over here. And I always like to begin with the color blending state. Call that color blend state. That is a vk pipeline color blend state create info. Color blend state. Initialize that to 0. And the structure types will be very long from now on. Color blend state dot s type, color blend state create info, color blend state dot. What do we specify here? We need, well, what do we need? We need what is called an attachment. And I don't know why that is this way, but the color blending is not specified over here, but in the attachment actually. And I'll show you what that means. The pointer attachment is a pointer to a, let's call this color attachment, and that is a vk color blend attachment state. vk pipeline color blend attachment state. I don't know why that is like this. Color attachment, if I can spell attachment, color attachment dot. And here we can specify how we want to blend alpha and color. But for now, we don't enable anything. So thankfully, we only have to do vk false because we want to get a triangle on screen, but don't want to do any blending. But there's one more thing that we need, the color attachment, and that is the color write mask, which basically says, well, which channels do we want to write to the image? And we want to write all of them. The red, green, blue, and alpha channel. And those are specified doing vk color attachment component. Let's begin with R for red. Then we vk color component G, vk color component B, and vk color component A. RGBA. If we don't do that, we don't write any color and we won't see our triangle. Trust me, I tried that and it didn't show up. In the color blend state, we also have to specify the attachment count to be 1. I'm pretty sure you can use more than one attachment here. I didn't have the use case yet. Probably there is a use case because otherwise it wouldn't make any sense. So that's the first one out of many. Let's put the pipe info.pointer vertex input state, vertex input above the color blend state, because this is usually what is happening first. vk pipeline vertex input state create info, vertex input state. That S type obviously will be very long. vk vertex input state create info. And basically that is it for the vertex input, because we won't be using that later as well. But also we don't have the use case yet. We won't be supplying the vertex data to the shaders. This is basically happening over here. This is like the vertex and the index buffer. This is like the data for our geometry. We have the input assembler. This tells the shader, well, what type of data we will be working on, which vertices, how many vertices, and so forth, right? This is like this stage. And I think this is a good way to start creating our first shaders. And what I like to do is I like to create a top root folder called assets. And in that folder, I like to create shaders. And in the shaders folder, I like to create a shader.vert and a shader.frag. Vert stands for vertex shader and frag stands for fragment shader. Let's start with the vertex shader. These shaders are written in GLSL. Basically in GLSL, you specify the hashtag version first. You have to specify that first. If you try to not supply that, you will get an error. The next thing you create is a void main function. You could call this function any way you like. It is just a good practice to call this main, since everyone does this, but you can do whatever you want, right? And what do we want to do in this function? Well, for every invocation of this vertex shader, we want to write the position of the vertex into a variable called gl_position. That is a variable, a vector 4 that you need to write to if you want your vertex to have a position. So basically that will be a vec4 out of some arbitrary positions. And one more thing, the vertex shader will be run for every vertex in the vertex buffer. Since we don't have a vertex buffer, what we can do is we can specify a vec2 array of vertices like so, which has a count of 3, and we can then specify what type of vertices we want to have in the vertex array. Let's create a vec2 for the first position. And this is where we have to look at the normalized device coordinates of Vulkan. Basically, Vulkan's coordinate system goes from -1 to 1, 1, and 0, 0 is in the middle. So basically, we want to create a triangle that looks like this over here. We want to specify the first vertex to be -0.5 in x and 0.5 in y down, then 0 on x and -0.5 on y up, and 0.5 on x and 0.5 on y. So basically we do -0.5 on x, and for y, since we go down, we do 0.5. That would be the first vertex. The next one is 0 on x and -0.5 on y. Then the next one, the last one, would be 0.5 on x to the right and 0.5 on y. And so the first part of the GL position of the vec4 will be from the vertices, and we can access those vertices at what is called a GL_vertex index. But those are only two components of the vec4. We have to specify the other ones too. The y will be 1.0 and the perspective divide will be 1.0 as well. Basically, I've been playing around with this value. You can make objects smaller and bigger based on the perspective divide. You can play around with this, like put this to 2 or put this to 0.5, and then you'll see the result. It's very fun to do so. But most of the time, this is 1.0. Okay, that is the vertex shader. In the fragment shader, we begin by specifying version again, version 450, and then obviously we do a void main. And in the fragment shader is invoked for every fragment. We have now done this stage over here, the vertex shader. We cannot program these shaders, but we can specify some stuff in the tessellation stage of the pipeline. We'll see later what we can do here when we get to that. So we'll skip those because we can't program these. In the rasterization state, the image is being rasterized into what is called fragments, and every fragment can have a value, a color value. And so the fragment shader is invoked for every single one of those fragments. So doing expensive calculations in your fragment shader can hurt you. If you can, you should do expensive calculations in the vertex shader, if possible. So yeah, that has been rasterized, the image, and then the image in the fragment shader is being colored. And then the color blending happens, which we have specified to do nothing yet. I know this is a very general overview, and obviously there's way more to it, but I hope this gives a general understanding of what happens. The most important thing is that the fragment shader is being invoked for every single fragment. And so the fragment shader has to write the color output. And we do that. We have to specify this layout location as 0. The first output is a vec4, and I always like to call this fragment color. Right? This is the color of the fragment. And in the main function, we just specify, well, what is the fragment color? And I will specify this as white for now. 1.0, 1.0, 1.0, 1.0. And in GLSL land, we don't have Fs. This should actually be it. And this too. We now have to compile the shaders. Luckily, Vulkan has a compiler for us because Vulkan won't read this code in. Vulkan what is called a spir-v bytecode. And we can create that bytecode by calling the glslc.exe. And you can find this exe by going to your Vulkan SDK folder in the version and then in the bin folder. And there you find glslc.exe. You can also use the glslang validator, but I like the glslc more because you can do some fancy stuff like include files in your shaders, and it will just include the code of the files inside these shaders, and that will allow you to do some fancy stuff like include a header file in the shaders and in your program, and with some clever defines you have shared structures in your program and in your shaders, which is very powerful and what we will do later as well. So I use the glslc, I copy the exe, and I basically open the file explorer where the shaders are, and I paste that in here. Then I open the command line and type in glsl.exe. I specify the first name of the file that I want to compile. I do -o for output, how I want to name the file, and that would be the shader.frag.spv for spir-v bytecode. Basically, we have to specify that we write out. We do, and that is a keyword. We have this out keyword here. I forgot that. And then this should compile. The next one obviously is the shader.vert, and shader.vert. Let's see if that compiles. That compiles fine. Now we have shader.frag and shader.vert SPV. These are the files that we need to load in our pipeline later. So in the pipe info, we have what is called a pointer stages. That is a VK pipeline shader stage create info. Remember those pipeline stages? We can specify the shader stages, the vertex shader and fragment shader stages in this structure. And this is what we need to do now. We specify, well, we have a vertex shader stage. It uses this shader, so this bytecode, and it uses this main function to start and all of that stuff. This is what we specify now. This is a pointer stages. And I like to call this shader stages. It will be an array. We can also use the stage count and do the array size of shader stages. And I guess we create that now. vk shader stage create info. Shader stages array. And we create the first one. vk pipeline shader stage create info. Call this vertex stage. Initialize that to 0 and the vertex stage dot s-type structure type pipeline shader stage create info. vk structure type pipeline shader stage create info. That's a big one. Vertex stage dot. What do we need? We need a pointer to a name, and this is the what I said earlier. You can call the function anything you want. We call this main function, so we specify the main name here. What else do we need for the vertex stage? We need to specify what stage this shader references, and this is the vk shader stage vertex bit. There's a lot of shader stages. We want to create a vertex shader here. And then the last thing that we need is a module, a vk shader module, which would be the vertex shader. And we have to create those, a vk shader modules. The way this works is you load the code of the shader, you create a shader module using that code, then you supply that shader module to the shader create info to the pipeline. You create the pipeline, and then you can destroy the shader module again if you know that you won't need it anymore. So we have the vertex shader and the fragment shader, and in order to create a shader module, we have to call vk create shader module. Takes in a vk context device, then a shader module create info, which would be shader info, allocator nothing, and then obviously the vertex shader. And let's do the same thing for the fragment shader. Let's specify the vk shader module create info. Call this shader info and initialize that to 0. Okay, the shader info. What do we need? S-type again, obviously. vk shader module create info. There we go. vk structure type shader module create info. Blah, 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 blah. Shader info dot. We need a pointer to code and a code size. This is the important stuff. Pointer to code. We need to load the shaders, meaning we need to load a file. And for that, we need a new platform call char pointer platform read file. Takes in a char pointer of a path and a uint32t pointer to length. So we can supply the length of the file and the buffer to the file to anyone calling this function. We will implement that over here, yank that, paste that over here. And this is basically Windows file IO. I do Windows file IO because first of all, it is educational and you get a little bit more freedom on what you want to do. So yeah, and obviously the educational part, right? So we specify a char pointer result be 0 first. And then we down here, we return result. So in case we could not read the file, we can check on the result if it is actually returning something. Then what we need to do in Windows is create file. This weird call takes in the path. It's basically trying to open the file based on the flags and the access that we specify. For example, what we want to do when reading a file, we want to do a generic read. And then there's a share mode, which would be file share read as well. Then we have security attributes. We don't need those. A disposition. This is something that is very important. Basically, this says how we want to open this file. For example, if we want to check if a file exists. If it doesn't exist, we want to throw an error. Or if it doesn't exist, we create the file and all of that stuff. But what we want to specify over here, if we want to read a file, we want to open an existing file. And this basically throws an error if the file doesn't exist, which I think is good. And then we specify no attributes and no template file, blah, blah, blah. In this file returns a what is called a handle in Windows. And I like to call this file because that's more readable. And then we can check on the file if the file is unequal to invalid handle value. And you can check on what that actually is. That's basically -1. If that is not the case, then we want to throw an error to do or log an error. So we basically want to do an assert here. And then we print out an error. But for now, we have the std cout failed opening file. Std end line. Okay, if we successfully opened the file, we now have to check the file size by calling get file size ex. And ex means basically that is an extension. Get file size before was not meant to work with 64-bit, and therefore they had to implement an extension, Windows by the way, that handles that case. So we have a file here, and then we supply a large integer pointer, a p large integer. That would be a pointer to size over here. And that would be large integer size over here. And for this call, it returns a bool. We can if check that bool. If that works, we are golden. If not, we do another to do assert, and then we do std cout failed getting size of file. Std end line. And you can see already the powerful stuff here is that we know exactly what didn't work. I don't think these can ever fail, but who knows? Maybe they can. And now it is time to do some stupid stuff we call new on the stack to allocate the buffer. So basically what we do is result is new char array using size.quad part. And I guess this warrants explanation. The large integer union in Windows is basically a structure that has a quad part to store a 64-bit integer. If you can't store the 64-bit integer, you can use the high and low parts. Basically what this is saying, the size is in the quad part of the structure. So we use that. What I like to do at this point is I have the length over here, so length, and I just assign the value of the size.quad part to the length. And obviously this will complain, so we cast this to a UN32T. This is not perfectly correct, I know this, because it might be that a file is way bigger than 4 gigabytes of memory. So if you want to make this correct, you should use a UN64T pointer here. For me, this is enough because I know I will not be opening files that big. Therefore, I supply the length over here to the new char. And I just noticed I can't spell length, which I can never do. Length with H, and over here to TH, please. After we get the size, we read the file. And the same thing with read file and read file AX. The extension is obviously the 64-bit part. I'm not using the extension part here because first of all, I won't have that large files. And second of all, the extension has a couple of different parameters, if I'm correct, EX. It basically doesn't have the number of bytes read, which is very nice to check against. So we supply the file handle, we supply the buffer, which would be the result. Then we supply how many bytes we want to read, which would be the length. And then we supply how many bytes we have actually read, which is a pointer to a D word, bytes read, and overlap is 0. And we can if check against that too. We throw another error to do assert and error checking. But for now we do std cout failed reading file, std end line. Oh, and we also have to specify the D word bytes read over here. If we successfully read the file, we have success and nothing happens. I don't know what to do in this case. One more thing we have to do, very important. when we open a handle to a file, we have to close that handle. And in the success case that we opened the handle, we have to close handle as well. It takes in the file. Boom. Let's hope that works. I always fuck this up. So now we can call platform read file. We take in the path, which would be assets shaders / shader.vert. And then we specify the length. And I like to call this size in bytes, like this. Obviously, we need to create that here. Size in bytes. And that is it. You can actually store that immediately in the pointer code. But what we have to do here is if we inspect the pointer code, or let's say the VK shader create info, the pointer to the code is a UN32T pointer. So basically, the data is being interpreted as UN32T numbers, the bytecode. And so we have to cast to that pointer. And we also have to specify the shader info.code size. And one would assume that you might have to specify the size in UN32Ts, meaning the size in bytes has to be divided by 4, or let's say the size of UN32T, but that is not the case, which is why I called this size in bytes. The code size is actually the size in bytes. Not sure why, but that's how it is. So yeah, then we create the Vertex shader and we are good. But I just noticed that this would waste memory, so we have to do something else. Call this char pointer code is this, and let's do it like this. Remove the conversion, and then we basically do, well, UN32T pointer code. And then basically after we create the shader module, we can delete code. We copy those two over here, do that as well, and yoink that too, and assign code again. Now this time we don't do the Vertex shader, but the Fragment shader. Create another shader module and delete code as well. Obviously, let's add the to-dos here. To-do sub allocation from main allocation. Again, this is me being me, and I want to practice this way of programming. But for demonstration purposes, I do it this way. But later on, we will have sub allocation from main allocation, and then these delete calls will go away. Okay, let me double check if I didn't forget anything. We can also do VK checks here. That's a lot of stuff to write. And I think now this won't work, obviously. But what we can do is check if we can actually create the shaders. Apply the Vertex stage over here for now. Try to compile. Let's see if I forgot anything. Looks good. Doesn't mean it will work though. And let's add a breakpoint over here. See if that works. So actually, seems like we managed to load the code. Yeah, it seems good. Oh, I forgot something. I just noticed we have been loading the wrong code. We need to load the SPIR-V code, not the shader code. So .spv for both of those. .spv. Build that again. Try to run. Do that. Interesting. Did it? Well, it didn't say anything. We delete the code, we read the new file in, and I guess we successfully have been loading both of the shaders and creating the shader modules. There's no validation errors, nothing. That's great. Now that's not enough, obviously. Let's basically create another shader stage over here. Call this frag stage. Or fragment. Yeah, let's call this frag stage. And over here, frag stage. Main, and this takes in not the vertex, but the fragment shader. And obviously, whoops. Obviously not the vertex stage, but VK shader stage fragment bit. Basically the same thing, but only for the fragment shader. And we supply that here as well. Stage. Boom. Now we have the pointer to stages and stage count ready. But obviously that is not everything. Now we could actually run the program right now and call VK create graphics pipelines. This would fail. But I think let's just try that and see what it does, right? Just for demonstration purposes, we call this call. It will fail, obviously, and then in the debug console, we see errors. For example, the pointer to rasterization stage cannot be null. It's the first one. And then we have a create info layout that is also cannot be null, and a render pass cannot be null. So yeah, when you do something wrong, Vulkan will tell you most of the time. So the pipe info dot. So basically, we need a rasterization state. Pointer to rasterization. Call this rasterization state. Very difficult to spell. VK pipeline. Rasterization state create info. Create info. That one. Rasterization state. Initialize that to 0. The S type is obvious. Structure type. Rasterization state create info. There we go. Well, what do we need? There is a lot of stuff. Polygon mode, line width, front face, def clamp enable. Basically, I've tried around a bit and gone through all the errors. What we actually need is front face. What is that? A VK front face clockwise or counterclockwise, meaning that whenever you specify the positions of your vertices, when going from one vertex to another vertex, that will be clockwise or counterclockwise, right? When you look at this. And the way we specified our vertices is over here first, then top, and then to the right, right? And then we go back to the first one, obviously. This is clockwise. And then we can say, well, okay, in the rasterization state, the culling mode is, well, we want to cull vk cull mode back. We want to cull everything that is in the back. Let's say this is our triangle, right? We look at it from here, and then in the back, if we were to look at it from the back, we would see nothing because this would be culled away. And this is what happens sometimes in games when you have like the flat surface and you turn around and you can see through the walls because you're not supposed to be inside a wall or something. This is basically culling. Those two are important. And depending on how you set up your renderer, culling can make everything invisible and confuse you. So yeah, this is oftentimes a very first step to look at if something is not drawn correctly. The next thing we need is a what is called polygon mode. We have 3 vertices, right? And what we want to do is vk polygon mode. And then we can specify, well, what do we want to do? We can do lines, and this would create a rectangle, but don't fill the rectangle and just create lines. We want to fill it though, so we do vk polygon mode fill. But you can experiment with these, and I'll probably do so as well, just to show you. And then there's the last thing that we need, which is basically line width. And this has to be specified as 1.0. If you don't do that, the validation layers down here will complain and tell you. I tried. So I'll just specify this 1.0, which is basically when you have a line, you don't do polygon mode fill, but polygon mode line, how thick the lines are, right? So yeah, and that is it. We supply that to the info. Boom. Pipe info dot pointer rasterization state is pointer to rasterization state. I already had that. Great. So didn't need that. Nice. Looking down here, we have the rasterization state done. We need a layout and a render pass. Well, in order to create a pipeline, you also need what is called a layout. And that is, remember how we written those 2 shaders? In the shaders, you can actually access textures or buffers on the GPU or maybe on the CPU, depending on where you create those buffers. But more on that later. And the layout specifies which shader uses which buffer in the memory. It's more or less like, well, it's using this pointer and all of that stuff. This is what the layout does. We don't have any layout yet. And so all we need to do, basically, let's create a new scope, pipeline layout, and call vk create layout. Pipeline layout needs a vk context device, layout info, pointer to that, another allocator, 0, and the vk context pipe layout. Let's call it that. Let's first do the vk pipeline layout create info, layout info, initialize that to 0, layout info dot s type again, vk rock type layout create info, boom. And the funny thing is, this is already enough. I tried that out and that works. So do nothing except for the vk check, of course, which would be this. And we specify the pipeline layout down here. Let's do some more spacing. vk pipeline layout, pipe layout. And then let's go back to the pipeline create info and do the layout, which would be vk context pipe layout. I guess we can put this all the way up here as the first thing. And then we also add the pipe info dot render pass to be vk context render pass. Oh, I didn't specify the pointer here. Do another check, run that. Check on the debug console, nothing is wrong. Means we successfully created this pipeline layout. Then we can do another one. Still doesn't work. Damn it. This time it is complaining that we don't have a pointer to a viewport state. And so I've tried around a bit. And basically what we will do is we will set the viewport and the scissors, which is basically, let me show you. Basically you can make your viewport any size you want. So the image that will be displayed in your surface, which is the window, could be any size you want. You could basically squash the image, or you could supply a scissor, which would break the image, cut it off, right? This is the right part here with a full viewport. But we will be using those dynamically, meaning that when we create the graphics pipeline, these are not very important for us because we will be setting those during the render loop. And the reason for that is that we don't have to recreate the pipeline whenever we change the window size. Basically when someone is resizing, because that will take a long time, recreating all of our pipelines. We don't want to do that. But we still need to specify that. And I don't know why, because let me show you the pipe info.pointer to viewport state, which would be the pointer to viewport state. Put this down here. VK pipeline viewport state create info viewport state. Initialize that to 0. Viewport state. Basically, this is the pointer to viewports we need, the pointer to scissors, and the count. So the count would be 1, then the viewport count would be 1, 2, and then the pointer to scissors would be scissors or scissor, and the pointer to viewports would be viewport. Put this down here, and then we have VK rect to D, which would be scissor, scissor. Initialize that to 0. We supply that. Basically, every single value is 0. The position and the size is everything is 0. And then we do VK viewport, initialize that to 0. And then we supply that. Oh, we forgot the viewport create info. Great. Viewport state dot s type VK underscore structure type viewport create info. We have to tell Vulkan that we are going to use dynamic viewports in scissors. And we can do that by specifying VK dynamic states. Dynamic states. That is an array that we fill directly with VK dynamic state viewport and VK dynamic state scissor. Once we have the dynamic state, we need to create what is called a VK pipeline dynamic state create info. Call that dynamic state. Initialize that to 0. And I need to learn how to spell state. Dynamic state dot s type is the same thing again. Dynamic state create info. And I know this is a bit dry because we create a lot of stuff and don't get anywhere. In my opinion, this is the craziest part of Vulkan, the pipeline. Once we have that, we will extract all of this away and then just control certain parameters that we are interested in. We just have to write this once, get it to work, and then abstract. This is more or less the biggest boilerplate in Vulkan, the pipeline. But this will also give us a lot of freedom in what we can do. So the dynamic state dot, what do we need? We need a pointer to dynamic states, which would be dynamic states over here. And then we need a count, which would be array size of dynamic states. And that's it. Then we supply that to the pipeline over here. Pointer to dynamic state, not states. And I guess we can run again and see if that works. It won't work, I'm pretty sure. It's still crashing. And this time it says that we need a pointer to a multi-sample state. It cannot be null. And then it says the pipeline topology is not set to point list, but point size is not written. And we need an input assemble state. So those two, we have to specify those in order for it to work. And if I remember correctly, those are the last two things we need. A shit ton of stuff, but once we have those, we are finally golden. So yeah, let's do the first one, the VK multi-sample state create info. Multi-sample state, initialize that to 0. The S type is obvious. VK structure type pipeline multi-sample state create info. Nice name. And basically what we say, what we need to specify is the sample count, the rasterization samples, right? The one that we specified earlier as well. How many samples do we want to take? And we do VK sample count 1 bit. And I tested that and we don't need anything else. Let's just do the next one too, which is the input assembly. So VK pipeline input assembly state create info. I like to call this input assembly. Initialize that to 0 too. S type is obvious. Again, VK structure type pipeline input assembly state create info. Let's look what we need. And there's one important thing, which is the topology. And that is interesting. What we can specify here is how we supply the data. For example, the VK topology, the primitive topology triangle list, triangle strip, line list, line strip, point lists. We want to have a triangle list. And basically what that means, the specification is always a nice point to look at. VK primitive topology point list specifies a series of separate point primitives. The triangle list specifies a series of separate triangle primitives, meaning that we can have separate triangle primitives on screen. A primitive topology triangle strip, on the other hand, would be a connected triangle primitive, meaning that, let's say we have 3 vertices, right? Or vertex that we want to draw, which starts here, then goes here, and over here. Whenever you have more than 2 vertices, the next vertex will be connected to the previous 2 vertices, meaning the one over here will be connected to this and this one and build a triangle. If we were to create another vertex, let's say up here, it would be connected to the top and to the bottom one over here and create a new triangle. That is a triangle strip, meaning that you cannot have separate geometry. So if we want to create more than one object in a draw call, we don't use strip, but we use lists. Obviously, there's more to it, and I encourage you to read the description if you want to use more, but we need the triangle list over here. We can do a quick check. There's some other stuff, but we don't need those. This is basically all we need. And now we need to specify those in the pipeline info. Pointer multi-sample state, which would be multi-sample state, and pipe info pointer input assembly state, which would be the input assembly pointer. Now let's do a VK check here as well. I'm pretty confident that this will work, but we'll see. Might have forgotten something. Boom. Oh, looked good. Could be... Oh, so no error. We successfully created a pipeline. That is good. Now, let's double check if we need anything else. We successfully created the pipeline. We begin the render pass. We end the render pass. So basically, there's no errors when running our program. That is good. Now to the last and final thing to get to actually draw the triangle. In order to save some time, I know that we have to specify the viewport in scissors now. Remember, I said we wanted to have them dynamically. So we have to do vk cmd set scissor, and this takes in a CMD, of course. Then the first scissor, which would be 0, a scissor count, which would be 1, and the pointer to scissors, which would be pointer scissor. We'll specify that in a second. The next thing is vk cmd set viewport, takes in CMD, the first viewport, which would be 0, the viewport count would be 1, and then a pointer to viewport. And we specify those real quickly. vk rect 2d, right, which would be the scissor. Initialize that to 0, and then the scissor dot extend. Width and height is very important. That is the vk context screen size, and then the vk viewport. Initialize that to 0 too. Forgot to supply a variable name. Viewport, and then we have a height and width, which would be vk context screen size dot height. Do the width too. And the one thing that we have to specify here is the depth, the maximum depth, which would be 1.0. The minimum depth will be 0, but we have to specify the maximum depth. And remember the Z value of 1. If we specify anything higher than 1, it would be invisible. So yeah, we set those two, and then we can finally vk cmd bind pipeline. We bind our pipeline that we took so long to create. We pass in the CMD, the pipeline bind point, which would be vk pipeline bind point, and we want to do graphics, and then the vk context pipeline. Now there's one more thing that we need to do. We need to draw vertices. Remember the vertex shader, how we access the vertex index? Well, we have to specify what we want to draw. So the vk cmd draw function, well, text in the CMD, says, well, how many vertices do you want to draw using this pipeline? Well, we want to draw 3 vertices. We want to have one instance, and the first vertex will be at position 0, and the first instance is also 0. And that, in theory, should be it, if I didn't miss anything up. Hopefully I didn't. Oh! And we have a triangle! Woo! And no errors. That is it. That is the triangle that we want to do. Boom. Obviously, we still get this annoying thing, which is like resizing the swap chain, a lot of that stuff. But yeah, our application runs. We have no validation errors, except for this one when we close the application. But that is a different story. Yeah, that is it. The next time we will do textures. Very simple and quick way to do textures. Then I guess we'll start abstracting more and more. We will also, I think, and next time we will also look at logging, a more proper way of logging, but we'll see. I will decide that. So now we are back to the Git stuff. Git add, git commit, edit, pipeline, and render pass to draw a triangle. Then we check out to a new branch, all4 underscore Vulkan renderer textures. Created a new branch, and then we git push to that branch. Git push -u origin all4 Vulkan renderer textures. And this is where we'll start in the next tutorial. If you like what I do, consider tuning into my Twitch. I stream at 10 AM Central Eastern Time, which is 1 AM Pacific Daytime. You can also support me on Patreon. I've set up a new page. Supporting means getting access to the game code that I'm currently working on, which is Cake's Tower Defense.